Okay, today's notes, we're going to come in, we're going to recap what you saw in the Desmos activity on amplitude, period, and vertical translation. I want to come in and talk about kind of what we would look at with our functions. Now, if we've transformed a sinusoid function and the transformations, the parameters that we were looking at in the equation, bx and then plus d. So we were looking at in the first Desmos what changing A did to the amplitude and the pattern, and what changing D did to the midline and the vertical shift up or down. And what we're adding in this discussion is what does changing the coefficient in front of the X do? And we do know from our previous discussions about transformations that this is related to our horizontal scale factor. And so kind of as a recap of that, when we look at the horizontal scale factor, remember our transformation rule. If I were going to do x old, y old, the original anchor points, what transformations have happened based on the numbers that you have in the equation. Now, the b that's here, the coefficient on the x, it's related to the horizontal scale. But remember that you always do the opposite for the horizontal transformations. And so the actual horizontal scale is always the reciprocal of that value. So, for example, if we had a simple example of y equals sine of 2x, then what we know when we take a look at the 2 is that we had a horizontal shrink by 1/2. And if we have a horizontal shrink by 1/2, that would tell us that the new period of this transformed graph is going to be not 2 pi, which it was originally, but pi, or half of what it used to be. So that's one thing to look about with your transformations. Also kind of adding in our vertical transformations, our A is going to multiply times our output, and then add our D. So the vertical transformations, remember, go on the outside and give us our scale factors for our A. So in this would be your vertical scale. And this one, D, would be your vertical shift up. But I will tell you that this B in the equation has a lot more meaning to it than just the fact that it's the reciprocal of the horizontal scale. Now, what you already saw in the Desmos activity, that typically what you guys were working with is that when you were looking at it, they didn't write it as B, they were putting it in as 2 pi over the period times X plus D. So they were doing this kind of idea of a different way of looking at the period. And so when we have that, so let's put it down here, B equals 2 pi over the period. So let's think about what this actually means. Now, let's remind ourselves that the period is equal to the distance along the x-axis to complete one cycle, or to complete one revolution. So you kind of in your head, every time I say cycle, I'm really talking about one revolution around the circle. Now, when we first started a trig function, our period of the trig function was 2 pi radians to complete one cycle of the graph. And so that was kind of how we were looking at that. And the reason for that original period being 2 pi radians was because the sine or the cosine, depending on which one we were looking at, the repeat pattern started after you had done one revolution around the circle. And one revolution around the circle is equal to 2 pi radians. Now, there's another important characteristic that kind of goes hand in hand with period. And that characteristic, I'm going to introduce it now, is something called frequency. Now, frequency is what we are looking at in terms of how many cycles you can complete in a certain distance. So Period is the distance along the x-axis to complete one cycle. Frequency is the number of cycles completed in a set distance. And so the idea of this frequency, hopefully you can really see this connection as we write this down. If period is distance for one cycle and frequency is cycles per distance, that you will see that they have a direct relationship to each other, or rather an inverse relationship to each other. The period is actually the reciprocal of the frequency. So the frequency is cycles per radian. I'll put this up here for our example. So the frequency for our parent graph would be one cycle every 2 pi radians. So that gives us the frequency of the graph. And also you do realize that frequency is 1 over the period is 1 over the frequency. They are reciprocals of each other. So the key fact that we have here that we want to know is that frequency is the reciprocal of the period. And so that's going to give us kind of a big fact, and we're going to use this to help us understand more about what B is actually telling us. Okay, now keeping that in mind, we're going to come back to our equation. F of x equals a sine bx plus b. And we're going to talk about what this b really means. Now, the first fact, so we're just going to jot it down over here, is that b equals 2 pi divided by the period. So if you know the period, then we can find b. And it's fairly straightforward. And that's what you did mostly in the Desmos activity. Now, in terms of the meaning of what we're actually doing here, let's take a look at our units. In this, you basically have this idea that 2 pi was the original distance along the x-axis for the parent graph before you completed one cycle. Now notice that when you're taking your 2 pi radians and you're dividing by this new period p, whatever it is, what you're actually doing is calculating the number of cycles completed in 2 pi. And so let's do a couple of examples and see what I mean by this. So for example, when you have, say, a period that is equal to pi for a transformed graph, if I were to look at that b, my b would be 2 pi divided by pi, or 2. Now let's think about that. If the period of the transformed graph is pi, then in 2 pi, I can complete 2 cycles of the graph. And notice that our b was equal to 2. Let's do another example. Suppose I have a period of, let's make it a little bit bigger. Let's make the period 4 pi for the transformed graph. Okay? In that case, b would be 2 pi divided by 4 pi, which is equal to 1/2. So again, if we're sketching this and we have to go all the way out to 4 pi for one cycle, okay, then my sine graph is going to look more like this. And then when we look in 2 pi, which is back here, how many cycles do we see in 2 pi? We see a half of a cycle. So that gives us one important meaning for our b, is that it's the number of cycles completed in 2 pi. So if you just take a graph and if you have 0 to 2 pi marked and you kind of count how much or what portion of a cycle is completed in 2 pi, that will give us our b. All right, the next fact that we want to talk about with this b, okay, which I talked about above, is the reciprocal of b is going to be your horizontal scale factor. And in your anchor point rule, x old, y old, you would do 1 over b times x old, and then your AY old plus D. Okay, so that tells us why we're doing the opposite in terms of transformation. If your B is greater than 1, let's do absolute value so we're not worrying about flips. If the absolute value of B is greater than 1, then that's a horizontal shrink. And if the absolute value of B is between 0 and 1, then that's a horizontal stretch. So that takes care of our transformation idea. All right, now let's look at how frequency is related to this. Since B equals 2 pi over the period, and remember that our frequency we just talked about is the reciprocal of the period. So kind of combining these two things together, if I take a look at this, then really if I rewrite that coefficient as 1 over P times 2 pi, then I realize that I can basically substitute in and make this, it's the frequency times 2 pi, which we prefer kind of to write it as 2 pi times the frequency. So this gives us another way of finding B, that if we know the frequency, and remember frequency is going to be how many cycles per a certain distance. And remember, another word for cycles is revolution per unit of the x-axis. So how many cycles does it take to complete? If we're doing this in radians, then it would be 1 cycle every 2 pi. So it's this idea that it tells us the frequency that's there. So given frequency, I can find what the coefficient is. Now, one thing to take a look at is coming down here, another important fact, and kind of relating this back to some of the applications we did at the beginning of the trig unit. Looking at this frequency, when frequency is revolutions per distance, or I must say it could be revolutions per time, could be revolutions per radian, and so on, that this really does have a direct relationship to something that we're going to talk about. And that, hopefully you'll remember, especially when I highlight the one that if we're doing this in revolutions per time, that you remember that this frequency is a measure of angular velocity. And angular velocity is something really important when we have objects that are moving around a circle, like we are with the unit circle, and we were looking at going 1 revolution around the unit circle every 2 pi. So if we start to put this idea or notion of speed involved in this, and instead of measuring going 1 revolution every 2 pi radians, maybe we're a Ferris wheel, and that Ferris wheel is kind of rotating around maybe 1 revolution every 2 minutes. So this would be its frequency, and that frequency is telling us information about the angular velocity of the graph. Now, I want to go ahead and I'm going to change this now from an angular velocity in revolutions per minute. Let's convert to radians per minute and see what happens here. So remember to convert from revolutions to radians. We would start with our 1 revolution every 2 minutes. We would multiply by, put 1 revolution in the bottom, 2 pi radians in the top, 2 pi divided by 2, or pi radians per revolution. So this is my angular velocity, specifically in the units of radians. All right, and then my last fact, I've already pre-filled in for you. One, make sure that you change this bottom here to minutes, because I think I had a mistake before I paused the video. Now, in this, taking a look at it, 1 revolution per 2 minutes is your frequency times your 2 pi, which is exactly your angular velocity. So notice that what this does is it tells us that the coefficient in the transformation in f of x equal to a sine of bx plus d, that coefficient is exactly the angular velocity of an application problem in radians per whatever your time unit is for the X.